Hi, everybody, and welcome to today's Alluxio office hour, Achieving Data Locality Using Spark and Alluxio with and without Kubernetes. My name's Allie, and I'll be moderating the office hours today. Before we get started, a few housekeeping items. One, if you do have questions throughout the office hours, we do have our Slack channel available. You can see the link right there, alluxio.io/Slack. It's our community Slack channel. It's where our community kind of hangs out. All of our engineers are there as well. So if you have any questions at all during the office hour, we encourage you to go there and pop those into the Slack channel, and we'll get them answered there. If you also don't want to go to Slack, you can ask your questions through GoToWebinar in the questions box on your control panel. So with that, I would like to introduce Ben. Ben's going to be presenting, I think, the first part of the office hours. So with that, Ben, please take it away.
Thank you, Ali. Hi, everyone. Good morning. I'm glad to be here to present together with Jiacheng about this new office hour. The topic is about achieving data locality using Spark and with Alluxio in and outside the Kubernetes environment. So we will talk about two different settings, whether you're using Kubernetes or not using Kubernetes. Yeah, so first let's introduce ourselves. My name is Ben, as mentioned by Ali. I'm one of the founding members on the Alluxio team, and this is my email. And co-presenting with me, Jiacheng is also a core maintainer for Alluxio, and this is his email. So for today's session, if you have any question, we strongly suggest you join the Slack channel and ask questions. The advantage for doing that is you can go back and also check with your answers, and also other team members, in addition to me and Jiacheng, can also help. So it basically has a lot of benefits. And also, yeah, so we were dividing today's session into two different parts. One is regarding setting Alluxio overview, and also how to run, basically, when you're running Spark with Alluxio in the environment, how does that help the data locality, just talking about internals. And the second part is about having Kubernetes in this picture, and so Jiacheng will talk through details about setting Alluxio with Kubernetes environment and how does that help to improve the data locality when you're running Spark in that environment, and what are the different challenges and how we solve this, and what are the limitations and also the plan to improve this stack. Without further ado, let me go to the agenda. This is what I mentioned today. So first, let me introduce briefly what Alluxio is. Assume some of you know briefly about Alluxio. This was a research project called Tachyon, originally from UC Berkeley MPlab, and led by the PhD student then, HY, or Haoyun Li, who is the CTO for Alluxio, the company. We found this company basically, we want to commit it to the open source project, and the company was founded in 2015 with the back from top VCs like Andreessen. So the mission is to build an open source orchestration layer for the cloud, and we see a lot of recognition on the road from different media publishers about to acknowledge what we are doing here for this open source technology. And as I mentioned, this was an open source project from day one, and today, after 4 years development, we have more than 1,000 contributors on GitHub and 4,000 GitHub stars. And the project itself is under Apache 2 license. So which is very, if you are working in the big data space, this is the most popular license people are using and most friendly license, one of the most friendly licenses. And we have Slack channel. This is where we strongly suggest to do office hour Q&A. And also you're welcome to contribute to our source code to our GitHub repository listed here. So regarding what Alluxio is, this is we call this a data orchestration layer. If you see this data stack, we have the computation on top and also the storage in the bottom. So data orchestration layer in the middle. It provides several benefits to data ecosystem. By providing a data abstraction, we can use the different popular data APIs, including Java File System APIs, the HDFS API, S3 API, POSIX, or some other REST APIs. So we build the data abstraction, so different applications, including Presto, Spark, or Hive, or TensorFlow, they can talk to Alluxio, talk to this data abstraction using their favorite data APIs. And on the bottom, we provide different adapters. So we can use the driver to talk to HDFS or different versions of HDFS or GCS or S3 or some other popular storage. And the adapter is transparent and also is hidden from the users. The users just notice that they are talking to an abstracted logical file system rather than particular like a physical storage or physical protocol to use the data. And on top of this data abstraction, we also provide different data policies you can use. For example, you can set a data policy saying, I want to cache the data for 3 days in the Alluxio layer. So this is something you can definitely do with Alluxio space. And also you can say, okay, I want to use my favorite data eviction policies or allocation policies. So my caching layer can be smarter in the data orchestration layer. This is also plug and play, and you can definitely extend the example evictor and the allocators to implement your favorite logic. Yeah, so basically by adding this new layer of indirection and abstraction, you get a lot of benefits by having more flexible use for the data and transparently use different data sources. And also, for example, you can use your favorite data format to access the data. So there's a lot of benefits by having this new layer. I won't go to details, but because today the focus is really about how we help Spark workloads to achieve data locality. If you are interested, we have a series of data online meetups and also office hours. You can definitely join for the future talks. So before we go to more details, I want to talk about why people want to even try Alluxio in the Kubernetes environment. What is the expected benefits by doing so? So imagine like maybe 10 or 15 years ago, a lot of people running their big data workloads using MapReduce on Hadoop stack. That pretty much means you're running within your Hadoop stack with a co-located HDFS as the storage. So that brings a lot of benefits because when HDFS is co-located with your applications like Spark or MapReduce, you can definitely get the benefits having data local. So one of the, basically, if you read the early paper from Google talking about MapReduce and GFS, so one of the main principle is to move compute to data instead of moving data to compute. And that's why that is what the Hadoop stack is modeled after, and that is why you can achieve good performance there. But with the latest movement, moving first like AI workloads, microservice workloads, and now also big data workloads to the Kubernetes environment, people typically they don't have a HDFS or something similar to HDFS in this stack. On top of that, people also use remote or separated or disaggregated storage, typically as a data lake to serve the workloads running in the Kubernetes environment. So we see a lot of, for example, using GCS or using, for example, the S3 as a data lake. And in these cases, the data is remote. It's a separate storage service. Now it becomes very challenging. How do you enforce or even implement data locality in the stack? So having Alluxio in the Kubernetes picture helps to achieve elastic data for elastic compute and with tight data locality. So first of all, Alluxio can help the data locality by bringing the data closer to, by running Alluxio itself in the Kubernetes stack. You can improve data locality because Alluxio can bring the data closer to a big data analytics or ML workloads. So the data can be cached and you can cache only the hot tables or hot data sets. So that's only the working set, and you don't need to bring the entirety of the data set to the Kubernetes environment. And it also enables high-speed data sharing across jobs. If you have if you build some pipelines and you don't want to always write the data back to S3, which can be slow, or you can encounter some consistency issues that you don't want to handle, then having a staging storage closer to the compute or even co-located with compute can be really helpful to improve the performance. So we have a staging storage layer for the compute jobs. And one more benefit for having Alluxio here is to provide a unification for persistent storage. The same data abstraction can be applied across different storage like GCS, or if you have also a on-premise data warehouse you want to access, you can definitely mount different data storage sources into the Alluxio data abstraction file system, this logical file system. So your applications can just seamlessly access, in fact, different physical data stores, but having the feeling they're just accessing the same logical file system. So in this case, this can greatly simplify the maintenance and also the development for the application. So if you want to read more about why you want Kubernetes and Alluxio you want Alluxio in this kind of disaggregated data stack in the Kubernetes environment, below this is a blog written by Dipti from Alluxio, and this is a great read, and I strongly suggest you read about it. Okay, next slide. Let's go to a little bit more technical details. So this is basically prior to Kubernetes. When you're running Spark and Alluxio both in a standalone mode, how Alluxio helps Spark to guarantee the data locality? So by the way, I would like to have this interaction, my presentation more interactive. So once you have any question, feel free to put it on the Slack channel, and we can just we can answer it from there. So this is the workflow if you want Spark, how it works. And first you run, and in this picture, we assume the data is remote. It's not co-located with the Spark workloads. So in this case, the user first run a Spark job by submitting this Spark application. And in a lot of cases, people are running in the YARN mode or Mesos mode, and then they have the cluster manager, so which will accept this job, this Spark job, and then allocate different executors to run the job. So this is second step. On the third step, the Spark job will launch executors and also assign tasks to different executors in this cluster. And inside this different executor, the next step is to access data and make the compute. And later on, they can just destroy this job and remove this node's executors. So this is like the case once the data is in the remote, like S3. You always need to go to S3 to access the data to feed your Spark tasks, and you always get no locality at all because you always access remote data. So this is how it works in a setting without Alluxio. So with Alluxio, there are a few things different here. So first, the Spark context will first talk to Alluxio, because Alluxio, we put Alluxio client into the application. So the Spark context has the Alluxio client, and this Alluxio client implements a HDFS compatible API, which also has the block location information inside. So the Spark job, before it's launched the allocated executors, it can go to the Alluxio service in here, the Alluxio masters, to ask, okay, I want this file with the certain blocks, and where are these blocks stored? Because Alluxio, in this case, we suggest Alluxio co-located with the Spark nodes. And in here, the Alluxio master may return to the Spark job saying, okay, block 1 is served on the host A, which is running a Spark Alluxio worker daemon. So in this case, and you can see because Alluxio worker is running directly in as a standalone mode, it's running directly on this host and getting the IP, for example, for host A, it's getting the IP 196.00.7 or on a different host with a different IP. So it will return the to the Spark job, and Spark context can tell and can influence the cluster manager like Yarn or Mrs. saying, okay, please allocate job, my executor and the task on the host A. The reason is because the host A has a worker, Alluxio worker with the local data, and then they can assign tasks to that executor to have the data local. So essentially, the takeaway from this slide is the client, Alluxio client, because it implements HDFS compatible API, so we can return the Spark job about block location information, and then because we have the master nodes, it keeps track of all this location information, and that will return the list, will keep serving the list of workers nodes that currently have the certain data cached. On the next slide, so assume we have the data Spark executor launched locally on this local host, on the host local with the Alluxio worker. And how do we ensure they recognize each other as the local, and then they can use some efficient data sharing mechanism here? So what happened is because Alluxio worker returns the host IP to the Alluxio master, and the Alluxio master tells the Spark, okay, here are different sets of Alluxio workers serving this block, and they can do the string comparison by or host name comparison, and can tell, okay, I do have a local worker on Alluxio worker local to my Spark executor. So the Alluxio client inside the Spark executor will talk to the Alluxio worker and say, hey, I know we're local on the same node. How about let's do something more efficient rather than just always use network to transfer the data? Let's do some trick. In here, it includes efficient data sharing mechanisms, including using local file system, like you can use the RAM disk, returning instead of having the data streaming the data to Spark from Alluxio worker to Spark executor, you can just point it out to a local file system pointer. In this case, for example, some directory or some file inside the /mnt/RAM disk, and the Alluxio client inside this Spark executor can efficiently talk to the Alluxio worker by streaming data, but reading the data directly from the local file system. Or there's another way called local domain sockets. In case you don't have this like for example, the local FS is not shareable, then you can basically use the local domain sockets enable efficient data sharing. It emulates the network interface, but the performance is much better than the local network interface. So in this way, essentially, we compare the host name to identify, okay, I have we have the worker local to me. And once that is achieved, we can use the short circuit access or local domain sockets to enable very high throughput data sharing once the Spark executor and Alluxio worker are on the same nodes. Any questions here? Okay, so let's have a recap. Essentially, with Alluxio in this picture, the Spark job can run first talking to Alluxio service to get to know where data is cached, and then it will influence with this data, with this information in mind, it will influence the cluster manager to allocate when allocating executors to launch executors with a local node, with local process serving the data. And once this assignment is finished, is achieved, Spark executors can access Alluxio with efficient high throughput data exchange by using the short circuit reads or writes, or using local domain sockets. So this is basically very efficient when you're running Spark with Alluxio in the standalone mode. But we see more and more that people are running for example, Spark, the latest Spark versions, they're supporting running Spark with Kubernetes environment. And we see more and more people running in a different environment. So having this workflow working in the Kubernetes environment is a whole new different story. And I will leave this to Jiacheng to talk about what Kubernetes is and how the data locality is achieved in that new environment.
Hey, Ben, we do have some questions that have come in.
Oh, yeah. Is there any question?
Yeah.
Can you read, because we do not see it here. Yeah.
Yep. Okay, let me just say it. How do you maintain data cache coherency across different nodes?
Okay, so the question is about data, I guess the data consistency across different nodes within Alluxio. So that's a good question. So Alluxio is basically providing a very similar, I would say the same semantics with HDFS. Essentially, the data is write once and read many. So once the data is written to Alluxio, it becoming available to different applications, it becomes immutable. So once the data is cached and the data within this file will not be changed anymore. So there's one caveat. For example, if I have the same file, if I have this file foo in Alluxio space and I rename or I remove this foo file and then create another file with totally different content under the same name, right? So in this case, because Alluxio has its own metadata service, which is implemented by the Alluxio master, and the Alluxio master implements a strong consistency semantics. So once the data foo is removed, the file foo, the first file foo is removed, the second file foo will have a totally different ID. So although it looks like the path is different, but the ID underneath is going to be totally different.
Okay, thanks, Ben. So Tom Wang has a question, but it's really long. So I'm going to unmute him so he can ask you. So Tom, go ahead. I just unmuted you. Tom, if you're talking, we can't hear you.
Can you hear me now?
Now we can. Yep.
Okay, great. Yeah, I have a question. So in our job, for example, we have Spark jobs that needs to access like millions and millions of S3 objects. So when we partition, right? So the different partition may access the same S3 object, for example. So in that case, how does in the executor, in the worker, how does Alluxio, that local client, help keeping so then basically you have the same S3 object need to be accessed by different workers, right? So how does Alluxio help in that regard? Because in your presentation, it seems if it's the same block from the same S3 object, it will be stored in the same host, right? So in this case, it needs to be accessed by different hosts.
So actually, the slides I'm showing here is super simplified. It's not really it's from maybe it's very high level. Essentially, so for two things. First, I think if you have a very popular object, it's going to be accessed by many different Spark workers, and it's likely, and you also have Alluxio workers co-located on this different Spark worker nodes, and it's likely you will have multiple different copies for the same hot data, because it's not necessary we only have one copy in Alluxio, but instead there might be multiple copies depending on the access pattern. But also on the second point, if the one data is, say, just like, for example, by accident, there's just like one copy for this data in Alluxio space right now at time 0. So later on, there are different Spark workers, different Spark executors reading the same data from the same Alluxio worker. So hopefully one will read from local, and others may be reading from remote. That is also supported. So after that is done, and all these different Spark executors, they have their own Alluxio client, and the Alluxio client will instruct their own local Alluxio worker saying, okay, sounds like this data is pretty popular, let's cache them locally. So that will be the default behavior unless you set more advanced features like, oh, I want no more than 10 copies for the same file, same data block in the Alluxio space, or I want no less than 2 copies. So there will be, this is also doable with the Alluxio, with Alluxio workers.
What about doing joins? If I have a pair of objects, let's say object 1 and object 2, and then object 1 join with object 3, they're all coming from S3, how would you provide locality for that? Because they are like a pairs of objects.
I think the data locality is provided on the based on data access pattern. So if there's it doesn't matter like it's in a pair or it's like a sequential access, but if this is a first access, then Spark will see a cache miss, and Alluxio worker will go to S3 directly to read the data, and in parallel or in background, Alluxio thinks, okay, you're joining both object 1, object 3, and seems like they are both popular, let me cache both. And in the background, they will just try to cache both objects in the same, based on where you access them, where you are accessing them. So I would say like it doesn't matter how Spark is, like it doesn't matter what objects Spark is accessing or logically how you're accessing these objects. But more important to Alluxio is the order, how you access this. So for the first access for object 1 and object 3, there will be a cache miss because the cache is cold. And after that, if you run the same query again, or maybe 2 different queries, one query touching object 1 only, and the other query touching object 3 only, and they will see the data cached in Alluxio space.
Okay, are you caching at the block level or are you caching at the S3 object level?
Yeah, that's a good question. So from user's perspective, you can think okay. So a short answer to that is there is a concept called block inside Alluxio, and that's the basic cache unit. But this block is unique to Alluxio. It has nothing to do with S3 because S3 has no concept called block. It has S3 only has objects. So it's really just like the granularity of caching, and also depends on your data access pattern. If you're sequentially access one S3 object, then it's likely we just cache all the units, all the blocks from this S3 object. Or you just access the first byte, maybe first few bytes, and the last few bytes from this S3 object. Then we will just cache the first block logically and the last logic block from this S3 object.
Got it. All right, thank you.
Yeah. Feel free to also raise questions on Slack, so you can always go back to see the answers. Yeah, for anyone else. Thanks. So I will continue here, and I will hand it over to Jiacheng.
Yeah, thank you, Bing. So, quick overview of myself. My name is Jiacheng, and I'm one of the core maintainers of this Alluxio project. And from here on, this is the second half of this office hour. We will bring you to the Kubernetes land, give you a Kubernetes overview, and see what have changed by this containerized environment to the Spark plus Alluxio stack Bing has just discussed. And then we will talk about how we achieve data locality in this new containerized world. So let's start from a brief Kubernetes overview in case like some of you are not super familiar with the concepts. So Kubernetes is an open source container orchestration system for automating application deployment, scaling, and management. And what does that mean? I'm going to list a few major benefits what Kubernetes has bring you. So by being a container orchestration platform, for example, I want to deploy my application, and I'm capable of writing my own container and try to deploy my application in terms of this container. Kubernetes helps you to deploy this application agnostically to what platform you're using. For example, you can create your platform. You can create your cluster in AWS, on GCP, or even have your own on-prem cluster. Kubernetes deploys them and manages them in the same way. By giving you service discovery and load balancing, that means it does load balancing across all applications, so you don't need to write your own load balancer. Of course, you can have your own smarter logic of load balancing. Kubernetes always provide the support to that as well. By giving you storage orchestration, that removes, that separates the two concepts of computation and storage, and by managing them separately, it gives you a lot of ease of deploying stuff. By giving you horizontal scaling, that means Kubernetes is capable of horizontally scaling up or down your application based on the resource requests and some limits you set smartly. By giving you self-monitoring and self-healing, that removes you a lot of the DevOps trouble you would possibly see, especially if you're having a very large-scale application. And also, it provides you the ability of doing automated rollouts and rollbacks. That's very helpful if you are managing multiple versions, multiple moving parts like submodules, and for example, your applications across regions, and if you're doing A/B testing. The Kubernetes also have some other benefits. I will recommend you to go to their website and check it out. I'm just listing the top ones that are most hot that people refer to all the time. And now we are going to, in the next step, we're going to give you some key terms about Kubernetes, which we will keep referring to when we are discussing the data locality in the Spark Alluxio tech stack. So starting with a node. A node is a VM or physical machine that Kubernetes manages. It's the physical machine that really runs your code. It can be a VM, of course. A container is a Docker image. I hope you guys are kind of familiar with the concept of Docker image. It's a lightweight OS and application execution environment, kind of capsulated, so you don't get interfered by the outside world. A container is a running image. Of course, Kubernetes supports other container frameworks, like, for example, Rocket, but in this discussion, we'll only talk about Docker. A pod is the smallest schedulable unit of one or more containers running together. Those containers running in the same pod will share some resources, for example, storage, network, etc. So here we see that the level goes as follows. A node can have multiple pods running together, sharing the resource, and one pod can have multiple containers, and they see each other and share the same concept, like as if they're running the same OS. Controller controls the desired state, such as, for example, I specify this controller to give me 2 copies of my application container. So what this controller will do is it checks how many copies I currently have of this pod. If it's smaller than 2, it's going to create me extra ones. If it's larger than 2, say, for example, for some reason I have 3, it's going to go ahead and keep the copy number as 2 by killing one of those. Of course, controllers have many types doing many different things. For example, daemon set, which we use for deploying Alluxio worker, it is a controller that ensures each node has only one of such pod. That exactly ensures that we are running Alluxio workers as what you know as a daemon process. A volume is a directory accessible to the containers in a pod. A volume has the same life cycle as a pod. That is to say, when the pod is gone, there's no reason you have this volume anymore. That is different from the concept of persistent volume. By being persistent, that means if you want something to be kept in persistence, for example, you have journals or you have a database, a persistent volume is where you go to like keep your data in persistency, independent of the life cycle of the pod. Okay, those are the key concepts of Kubernetes that we will currently we will frequently refer to during the following part of the discussion. And now we move on to the Spark Alluxio stack in Kubernetes environment. Let's start with what Spark has changed when it's moved to the Kubernetes architecture. As been talked about, Spark didn't work with Kubernetes from the first day. It was added to Spark 2.3, which was 2018 February. By being native, that means the Spark application is able to run in Kubernetes as a custom Kubernetes controller. For example, at the client side, I do a Spark submit and submit my job. Spark submit is going to talk to Kubernetes API server, Kubernetes scheduler, which are native Kubernetes components, and they will start with creating the Spark driver pod. As you can see here on the right-hand side of this picture, it's running on Node A. And actually, it's this Spark driver that will do the following job, including creating the Spark executor pod. I hope you are familiar with I hope you remember the term Spark executor. And the Spark driver will give computation jobs to and collect the results from those Spark executors. And when the application completes, the executor pods will terminate and get cleaned up. However, the driver pod will persist logs and remain there in the completed state instead of just disappearing with all your results gone. Okay, and that's that for the Spark architecture on Kubernetes. And what do we have when Alluxio is part of the picture? In order to provide data locality, we choose to deploy Alluxio in the same way, which is called colocation. By the term colocation, we mean before Kubernetes, we deploy Alluxio worker process on the same node as where the Spark executor will run. That means there are two processes running next to each other, so they share resources, so they can see each other and communicate with each other locally. In the Kubernetes world, the only difference is now instead of processes, they are running in pods, which is a more containerized environment. Back to the life cycle, I hope you remember that Spark executors are ephemeral in Kubernetes environment because they are created and terminated by the Spark driver, and their life cycle depends on the application. However, Alluxio workers are different. Alluxio workers can serve cache across all the Spark jobs, and therefore we recommend people to make Alluxio worker a long-running process, so it's able to serve many Spark jobs that are run on this worker node, and even serve cache to different applications running on the same node as well. That decides the deployment order. We deploy Alluxio cluster first. That means we deploy Alluxio masters and workers. We use, remember, the daemon set to deploy one Alluxio worker pod on each node. And then on the client side, we can just Spark submit to launch the Spark drivers and executors. So in this way, the Spark executor will be launched on the worker node, which already has the Alluxio worker running. In that way, in that order, we achieve colocation. And that's the basis of the whole data locality story. However, in this Kubernetes world, we see some challenges brought by this new containerized environment. The first challenge is now the Spark driver is not able to allocate the executors correctly without smart configuration. And why is that? See, in this new environment, we have Alluxio workers running in pods. In Kubernetes, a pod will have a different host name and allocated virtual IP by Kubernetes. So you can see here, now the host name of the physical host is host A, the IP is 196 something, and the Alluxio worker pod has a host name of, for example, Alluxio worker pod A. And this IP 10.0.1.1 is a virtual IP allocated by Kubernetes. Nowhere recognized that. And block 1 is currently cached on worker pod A, and block 2 similarly cached on worker pod B. And now when the Alluxio client on the Spark side, on the Spark application side, ask for, hey, where is my block A? Where is my block 1? Alluxio master will only know that it's on something called Alluxio worker pod A, which is the Alluxio worker host name. It has no knowledge that Alluxio worker is now running in a Kubernetes environment, and this host name mismatch will lead to problems. And the problem is when Spark asks the Spark driver to try to allocate the Spark executor on Alluxio worker pod A, there's no node called Alluxio worker pod A, and it's just impossible to launch the Spark executor there. And now the data locality is not achievable. This is the problem. Our solution was, why don't we just launch the Alluxio workers with the same host name as the physical host? This is actually achievable in Kubernetes by defining host network equal to true, which is a Kubernetes configuration property. And by defining this, the node will share the network adapter with the pod. So this pod will have the same host name, host A, and the same IP, for example, 196.0.0 something. Now Alluxio masters are able to provide the correct advice per se, and Spark context will then try to allocate the Spark executor on this host A, which will be successfully found and identified as a node that is able to schedule a Spark executor. So problem solved, we reach the same locality as before. The Spark executor will be scheduled next to this host A Alluxio worker pod, and they can then start their journey of data locality. However, we have more challenges. The next challenge is, even though the Spark executor is scheduled next to the Alluxio worker pod, it fails to identify that Alluxio worker pod next to it. It doesn't know that the Alluxio worker pod with the host name of host A is a local Alluxio worker. And why is that? That's actually because of the same reason. Spark executors are scheduled without using the host network. Therefore, it's going to have a different host name. For example, in this case, Spark executor pod 1. And when Alluxio client asks Alluxio masters for where is my block 1, Alluxio master, of course, it gives it a list which has a single element of host A. Alluxio client will compare this host A to its own host name and see, hey, host name host A is not equal to Spark executor pod 1. And I don't think this is local, so I don't think I will talk to it as the local worker. So there's no data locality. This is challenge 2. Before talking about the solution, I want to bring up another challenge because we solve these two challenges together. The challenge 3 is, even if the Spark executor is able to identify the Spark worker as a local host, on the local host, they still have no means to talk to each other because pods don't share files in Kubernetes. They act as if they're two separate machines, and they don't share any local files at all. Remember, Bain mentioned Alluxio achieves data locality, and one way of doing that is to use this domain socket, which is currently at /opt/domain inside this Alluxio worker pod. This is a file only local to the Alluxio worker pod, and Spark has no idea where this file is and how to talk to it. How do we solve these two challenges together? The solution, I know it's a bit long, but I will break it up for you. The solution is, first we use a UUID to identify the local Alluxio worker, and then we share a host path volume between the pods to share this domain socket. Now we use a property, a new Alluxio property, to configure that Alluxio workers have UUIDs. And UUID means universally unique identifier, which is unique. Now this Alluxio worker has a UUID of, for example, UUID ABC, and in the same way, it has the host name, host A, same as the physical node. It puts its domain socket file, which is at this path /opt/domain/UUID-ABC in the host path volume, which means you put this file in the host, in the physical host of this node, and this node is a volume that's mountable to different pods. It shares the domain socket by this host path volume with Alluxio executor pod. So whenever Alluxio client in the Spark executor asks Alluxio masters for advice, where's my block one? Alluxio master will give it the list of single element, host A, but this time this new information, UUID APC, is provided together with the worker information. So Alluxio client will then go ahead to see, do I have a domain socket file somewhere? I have this mounted to my executor at this /opt/domain/UUID-ABC, and hey, it matches with this advice Alluxio master has given me. So that must mean I have this local Alluxio worker pod. And then why don't I just talk to this local Alluxio worker by talking to this domain socket? And in this way, we achieve the communication between the Spark executor and the local Alluxio worker and achieve data locality. In order to achieve this, we made two changes. One is at the Alluxio side, we added another Alluxio property called this. I mean, if you're not familiar with how to set it, we have this in the additional resources, so don't worry. The other change is we enabled the Spark to mount a volume to Spark executor at creation time. This is our contribution to Spark 2.4 by our engineer Adit. The PR link is here, and if you're interested, you can go into it and check. So after making those changes, we achieved data locality in Alluxio Spark stack. However, before I wrap up this office hour discussion, I want to briefly talk about the recap of Spark Alluxio architecture, the new architecture on Kubernetes. If you compare it with the previous architecture Bing has shown you, all the steps are kind of identical because we made those changes and resolved those challenges, so the architecture stays the same, basically easy for you to understand. The recap is we helped Spark schedule compute to data locality, to data location, and in the step 4, which is the compute step, we enabled Spark to access the data locally, which is a great boost to data performance. However, there are still some more limitations and the future work we need to resolve. The limitation is many enterprise environments have a strict control over host network and host path because it uses the resource at the host level, which is kind of beyond the control of containers. Alluxio workers need a host network to work because they need their host name to match with the physical node. We are currently working on some workarounds like supporting container network translation either in Alluxio or in Spark. The other one is the domain socket file requires a host path volume, which is also a host resource. We are currently working on workarounds like investigating other persistent volume options for us to use. For example, this new one added by Kubernetes 1.14 called local persistent volumes. And as said, we welcome all the feedback and collaborations from the community. So please let us know if you have new ideas and great insights about how these can be solved as well. And here's some additional resources for you to read if you are very interested in what we talk about today. And I guess we are moving on to the Q&A session.
Yeah. Feel free to ask the questions. We'll be still here for a few more minutes.
Okay, so there's a question that came through. What about overhead involved with Kubernetes and containers compared to running the application directly on a VM or a node? How much is that overhead?
That's a good question. I mean, actually, that question has multiple parts. The first part is, what is the overhead of running an application in containerized environment instead of running in a VM? That goes to some of the basic concepts of how can a container help you to boost up your performance. One of the major differences, if, for example, you are running multiple VMs on the same machine, you are spending a lot of additional resources by having those duplicated copies of your OS. Basically, each VM has an OS. They don't share anything with other VMs. That's kind of a waste of resources compared to if you're running multiple containers on a physical host, they actually share the OS together. And if they have similar layers, they can even share more. I would recommend you to explore how container, the concept is different from a VM. And back to the second part of the question, which is Alluxio in terms of containers and in the VMs. The difference is mostly identical, I would say, because the major concept of moving to a containerized world is to reduce the additional resource cost being by having multiple VMs. I hope that answers your question.
So I want to have a few points added. So one key difference, what we see is in the non-containerized environment, Spark and Alluxio can share data across local file system. That's what we call the short-circuit read and write. And in a containerized environment, we have to use the domain socket because local file system is not achievable, it's not accessible. And so that might be in terms of performance, that can be the key difference here. But what we see is with domain socket, the performance is actually pretty large. Like for a IO intensive workloads, that should be sustained. That should be good enough to sustain the IO intensive workloads. And I don't think you're going to be bottlenecked by the throughput of domain sockets. So yes, compared to the maximum throughput, writing to a local RAM disk can be higher. The throughput can be higher, but I don't think that's going to be a real in the real workloads. Okay.
Okay, I think that's it.
Great.
Yeah, so feel free to join the Slack channel, and we can definitely hook more on the questions you have more. And also, I and Jiacheng are constantly curating the questions on Slack channel. Feel free to engage with us for any future questions.
Okay, great. Thank you both for an excellent presentation. And as a reminder, this was recorded, so you'll receive a copy of both the slides and the recording. Thank you guys, and we'll see you next time.
Thank you, Ali. Thank you, everyone.